All right, we're back. We're on Calc AB Notes 23. This will be page 7. We're talking about slope fields, and this page has a little bit of a summary on it, and that's probably a good thing because it's never bad to stop and summarize. So let's see. For each of the differential equations below, along what type of lines will the slopes remain constant? Okay, so this is a big deal. I have issues with horizontal and vertical lines, so I have to go through this thought process every time. So I'm going to kind of write out my thought process. Dy dx equals f of x. Okay, so there is no y in the equation. That's my first thought. So if there's no y in the equation, then moving up and down doesn't change the slope. So this, I have to go through this every time. So moving up and down doesn't move the slope, doesn't change the slope, which means slopes are constant along vertical lines. That's what that means. Therefore, slopes constant along vertical lines. All right, so that's the process I go through. I'm going to go through the same process here as if I didn't just do that. All right, so what do I think? I think there is no x in the equation, which means slopes don't change moving left and right. And if they don't change moving left and right, then they're going to be the same along horizontal lines. So same slope along horizontal lines because the x value isn't impacting it. So if the x value isn't impacting it, you move left, you move right, doesn't make a difference, you get the same slope. So if dy dx is a function of just y, then along horizontal lines, you will get the same slope. Along vertical lines, you would expect the slope to change because the y value is determining the slope in some way or shape or form. All right, so I think I navigated that without confusing left and right, and up and down, and horizontal and vertical, hopefully. All right, when you look at a slope field, what are you really looking at? So you are really looking at, it's hard for me to make to write the word at anymore. I use the at symbol so frequently. You are looking at the solutions, all possible solutions to the differential equation. Excuse me. And I always abbreviate that as diff-EQ. So now when students come back to visit, they always call it DEs, but I always call it diff-EQs, and I still think that sounds cooler. So you're looking at all possible solutions to the differential equation. So how can you use that? Well, there's a lot of ways, right? Features, things like that. In particular, if you can guess a solution, and if you do enough of these, you can guess the solutions. If you can guess a solution, you can use it to figure out the differential equation by taking its derivative, which is kind of the link. So that's really interesting, and I've done that a couple of times. I did that on the last page with all the sine, cosine, negative cosine. I drew all solution curves, and I was like, basically, I'm done. I already know the answers. So that's definitely something that we can do. You also get a general idea, right? Like, where is the slope positive? Where is the slope negative? Where are the solutions increasing and decreasing as a consequence? Where do you have relative maximums, relative minimums? Think about concavity. There's all kinds of stuff. So what sorts of things should we consider when comparing slope field to a differential equation? Literally all the things I just listed. So it's really disappointing that I didn't read this question ahead of time because I could have just done that. So comparing a slope field to a differential equation. So I'm going to say sine of the slope at a point or in a quadrant. That can be effective. Zero slopes work really nicely. Linear solutions, because you can almost, what does that even say? Linear solutions, let's try that again. Linear solutions are easy to find. They're easy to identify in the slope field, and then you can verify them potentially. That's a really good strategy. What else is a good strategy? I don't know. Think about everything. Like why would you not try to think about everything? Is it just X or is it just Y? Is it a function of just X or Y? That can be incredibly useful. Just everything that we've talked about, just, know everything, it's not a very useful answer to a question, but I think it would be the best thing to do. All right, on the subfield below, sketch one of each type of solution curve that seems to fit the field. Next to the field, write what each type of solution curve has in common with others of its type. Okay, this is a good question. I'm going to start off with, I look through the field and I think I see a linear solution. So I'm going to try to do that. I don't know turn this into a line. And there, okay. So I think that the first type of solution, I'm saying type because it's the only one of this type. The first type of solution I think is the line y equals 1 minus x. I think y equals 1 minus x is the first type of solution that we're going to get. Now, it is just what it is, right? So, I mean, I guess like dy dx equals -1. What else? I don't know. This solution will be the dividing line between other types of solutions. Also, if we find the second derivative of the differential equation, right? So the differential equation will be dy dx equals blah. If we find the second derivative and set it equal to 0, we will get y equals 1 minus x because the concavity of this, so I guess I could say that. I'm going to say that the second derivative is equal to 0 because that's an important point. And maybe if we have time, I don't even know what it means to have time. Maybe if we have time, I'll actually like do that for this one. Did I crash this? I think so. Hold on, I'll be back. Okay, we're back. All right, let's take a look at a second type. So for this, I'll use a different color. I'm gonna do the decreasing type. So what should happen is you start along this, and then you just kind of do this. The closer you start to the asymptote up on the left, the longer it's gonna like ride along the asymptote and then like fall off eventually. So what's true about this? So type 2, I'm just gonna color code them so that you can like see it. For type 2, I think they are decreasing. I think they are concave down. I think that they have y equals 1 minus x as an asymptote. And well, not at, I'm gonna say as x approaches negative infinity. For all of them, the limit as x approaches positive infinity is negative infinity, which like, I don't know if I need to write that, but it is a property. They don't appear to have a maximum or a minimum. Just a lot of stuff like that. Let's look at the next type. The next type I think is like the most interesting of the types, but that's just a personal bias. Really, the linear one, which is the least like interesting looking, is probably the most interesting because it is the dividing line between concave up, concave down. It's the asymptote of all the other types of solutions. It's got a lot going for it. Like you can make a strong case that it is the most interesting. I'm going to start at this point, and if I go this way, just kind of follow. I think it'll go like that, and then this is going to be tough. Oh no. I'm gonna go in a couple shots here, I think. The problem is like I'm writing basically backwards. I'm holding my stylus really weird when I do this. I think that's a pretty good representation. Okay, so what do these all have in common? Well, they definitely have y equals 1 minus x as a slant asymptote. So that's good. I think they will all have a relative minimum. It's actually the absolute minimum. It's more annoying to show it's an absolute minimum than to show that it's a relative minimum. They all have a relative minimum. And then where does that relative minimum fall? So if you look at where the 0 slopes are, it's like here, 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 you can actually work out the equation of this line because it's happening like at really nice points. I think that it's 2 minus x. I think they actually all have a relative minimum along the line y equals 2 minus x. So I'm not going to prove that. I mean, I really want to prove that. And to prove that, I would say that show that dy dx equals 0 when y equals 2 minus x. And then show that dy dx is, not that dy dx, show that y is concave up at that point or along that line would prove that there's a relative minimum. But they all have a relative minimum along that. The limit as you go to infinity is infinity. I don't know, concave up is a huge thing. They're all concave up. And I mean, I feel like that's what I'd really want to see if I ask someone to describe it. You can't do much better than that, I don't think. So the differential equation is actually this. It's actually given to us. So this is our differential equation. It's actually x plus y minus 2. So we won't learn exactly, this year you won't learn how to solve this. Next year, if you're in my Calc CD class, you will. If you're in Calc BC, you also will not learn how to solve this. This is not an AP thing that you would have to solve, but you do need to know how to work with it, come up with a slope field, like identify characteristics of the slope field. So I said that y equals 1 minus x is going to be the dividing line between concave up and concave down. I just want to like show that. So given this differential equation, the second derivative is going to be 1 plus dy dx. And then dy dx is this thing. So that's going to be 1 plus the quantity x plus y minus 2, which is, so it's 1 plus x plus y minus 2, 1 minus 2, so negative 1. I'm going to say it's like x minus 1 plus y. So if the second derivative equals 0, that would mean that y is equal to 1 minus x, right? So take the second derivative set equal to 0, subtract x, add 1, you get y is equal to 1 minus x. If the solutions are concave up, so if we want the second derivative to be greater than 0, that would mean that we want x minus 1 plus y to be greater than 0, which would mean that we want y to be greater than 1 minus x. So anytime y is greater than 1 minus x, the solution curves are going to be concave up. If we want concave down, we just flip the inequality anytime y is less than 1 minus x. And you can see that in the slope field. You can actually identify it. So if it says, for what's the relationship between x and y when the solution curves are concave up, I would say that y is greater than 1 minus x. You get concave up. And I would prove it by doing this whole second derivative thing. So that's why I wanted to like do that. I don't think it's actually in the notes at any point. It totally should be. I should probably rewrite these, except I'm spending hours making these videos. So at best, I'll probably do a supplementary video at some point on that. But that's it for this page. So I'm gonna wrap this up. I will come back in the next video and do a little bit more. So I will see you there.